Hi everyone. Am I audible? Can anyone just confirm? You can type in the chat box if I am audible. The recording for this session has started. So you can't hear me? Anyone just confirm? If you can hear me, fine. So I believe my audio is clear. Let's wait for a few more minutes so that everyone can join and then we'll start this session. Hi everyone. Let's start today's session. Yeah. Hmm. Let's start today's session. Problem solving through programming in C. And let me share my screen. Screen, entire screen. Share. Yeah. Every one of you can see my screen, no? If you can't, just type in the chat box so that I can confirm. Otherwise, we may start. Anyone who cannot see my computer screen? So yeah, I believe every one of you is able to see the screen. You can just type in the chat box to confirm, and then we'll start this session. So solving through programming C. This is week 11. So we have already done 10 sessions till date. So everyone, can you see my screen? Am I audible? Are there any issues? Technical glitches? Yeah, you may just tell me. Otherwise, I'm not seeing any responses. Okay, fine. So let's start. So this is week 11, and we are moving to some advanced topics. So, anyone who has any doubts regarding all the topics covered in the previous sessions, you may ask me. I hope by now you all are able to solve problems using C programming language. So you are able to formulate some complex algorithms and solve them using C. So in the previous session, we discussed about linear and binary search and the time complexity. What is the time complexity of these algorithms? Then we saw what is a bubble sort algorithm, and then we saw what is a bisection method and how to find roots of a polynomial of a function and using bisection method. And then next thing that was using pointers and using pointers to pass references into functions. So any one of you, if you have any doubt related to these topics, you can type in the chat box. So right now I will like give a few minutes to ask you guys questions on the topics that you have missed from the previous session. If you have doubts from the earlier sessions, from sessions 1 to session 9, then I will be giving you time after 7:30. That is 1.5 hour after this session. Then you can ask questions from those topics. So anyone who has doubts in bubble sort, mm, and then binary search, and the pointers and functions in C, then you can type in the chat box right now. If you have any doubt with these questions, I will help you out right now. Otherwise, we can proceed further. So yeah, if you have any doubts, just type in the chat box. So fine, I believe there are no doubts. So let's proceed with week 11. So I am Rupesh Kumar, and we have these sessions every Friday, 6 to 8 p.m. So I hope you enjoy, and I'm able to help you guys with programming in C. So there are fewer topics that we will be covering in this session. So as continuing from the previous sessions, we will be looking at few more numerical methods that we use to solve certain problems, and then we will see how to code those numerical methods into the C using C programming language. So basically, we'll be talking about carrying out integration over the compute using programming. So for that purpose, we will be using the Rangakuta method. We will be seeing at the Rangakuta method that is able to uh, that's used to solve differential equations. Then we'll be looking at what is interpolation. So yeah, the order will be reversed. So first we will be looking at interpolation, and then we'll be looking at the Rangakuta method for solving the differential equations. And we will solve some problems based on these methods. And lastly, we will look at recursion. What is recursion? Why do we need recursion, and how we solve problems using recursion in C? Fine. So let's start. So the first question says, interpolation provides a mean for estimating functions at the beginning points, at the ending points, at the intermediate points, or none of the mentioned. So anyone, can you answer the question? I believe the lecture slides are updated. Just type in the chat box. So interpolation provides a mean for estimating functions. So yeah, interpolation is used for estimating functions, but where? At the beginning points, at the ending points, or at the intermediate points, or at none of the mentioned. So let me draw a picture for you. Sketch. Hmm. So let's say we have a function like this. So let's say this is the x-axis and this is the y-axis. And we have a function. Let's say we want to plot a function y equals to x. It's a pretty basic function that goes from the origin, and we are only considering the values in the first quadrant. Let's say we have these data points. So how to do this? So now let's say we want to find the value uh, at a particular data point that is not known. So let's say these points denote the data points at which the values are known. So, uh, so let's say for this x, we know the value y. For this x, we know the function value y. Similarly, for this x, we know the function value y. And for this x, we know the function value y. For this x, we know the function value y. And let's say we want to find the function value for a particular input that is unknown. So let's say we want to find function value at this point. So what would be the function value at this point? So this axis represent f of x, and this axis represent values x. Fine. And these are the known values. So we know the values at these points, and we don't know the function value at the remaining points. And let's say we want to find the function value at a particular point. So how can we do this? So we can do this using interpolation. So we can fit a function over this set of data points to approximate what the function would look like. And one of the most basic example is the easiest example is linear interpolation. So what do? We assume that these points are lie in a line. So these two consecutive points lie in a line. So this function is basically a line, then this, and then this, and then this. So we approximate the function using a line, and then we can find the value of function along this line for any input. So let's say we want to find the value at this point. We have approximated this section as a line joining these 2 points. It's a straight line joining the function value at this point and this point. So everyone, are you following what I am explaining right now? Is it clear, or should I use a different method of explaining these things? Please type in the chat box if it's clear, whatever I'm trying to explain here. So we are discussing what is interpolation and why do we need it. So here we have a function like this. We have some data points. Let's say 1, 2, 3, 4, 5. And for these values, the function values are known. So these are the values at these different points. and we want to find function value at some another point like this. Let's say this point number 6. We want the function value at point number 6. So for that we use interpolation. So we essentially approximate the function using a particular using some convention, and then we use that function to approximate the value. So everyone, do you is it clear, or I'm confusing you? So I wanted to ask. You can type in the chat box because I can't see any messages from you. So if it's clear, just type in the chat box that it is clear. If it's not, then I will explain it in a different way. Oh, fine, great. So yeah, so how do we approximate this function? It depends upon us. There are various methods to do so. And for this example, let's say we are talking about linear interpolation. So for linear interpolation, what is the convention? We assume that these points lie in a line, and then we try to find. So let's say we want to find the function values across this segment. Then what we do, we draw a straight line joining these two known points, and then any value between this, the function value of around any value in this segment can be computed using this line. So this is what interpolation looks like. So you know the values at the ends, and you want to compute approximate the values at this between those given data points. So what, let's see what the function says. Interpolation provides a mean for estimating functions at the beginning points. No, because we know the beginning points. Also at the ending points. No, because we know the ending points. At the intermediate points, so that's the option C is correct. So the correct answer for this one question is option C. So it option C. So basically, interpolation provides a mean for estimating functions at the intermediate points. You may find its applications in various ways, because whenever we represent data onto a computer, we you discretize it and then represent it. So wait a minute. So yeah, there was an interruption. So yeah, I will let's take a break for a few minutes. I'll rejoin the meeting. So apologies for the inconvenience. So yeah, let's restart. Apologies for the inconvenience. So yeah, this is what interpolation looks like. So we were discovering what is interpolation, and interpolation is a way to approximate function values at intermediate points, and it is used for, let's say, it's used in various applications. Let's say you have discretized a function like this. So let's draw a new plot. So let's say we want to store values of a sine function in on a computer. So we can use a array to represent the function values. So this is x, this is the x-axis, and let's say the y-axis represent. Let's make it a bit more straight. Right? So yeah, so this is the x-axis, and on the y-axis we are representing sine x. Let's say sine. Fine. So what does sin x looks like? It looks like this. It's a wave kind of like of structure. And so also it goes on. Fine. So it goes on like this. So let's say we want to represent this function values between the origin 0 and let's say this is 0 pi by 2 pi pi 2 pi. Let's say we want to store the function value between these 2 points 0 and 2 pi. So we don't need to store other values. So we may discard them. So we want to store the function values between these points. Then how would we store these values on a computer? So in C program, let's say we want to write a C program that stores the sign values of sign function at these different points. So what we do, we discretize it. So essentially, we can't store continuous values in computers. We can store this using arrays. So let's create a two-dimensional array for this purpose, like this. Fine. And let's say we store x value here and the sign value here. Then sign of x. Fine. So at 0, it is 0. At pi by 2, at pi by 2, it is 1. At pi, it is again 0. At 3 pi by, sorry, at 3 pi by 2, it is -1. And at 2 pi, it's again 0. So let's say we are storing the sign function like this onto a computer and are using a two-dimensional array. Oh, where is the is it? So this is the two-dimensional array containing the that stores the sign function. And now what happens? We have stored this sign function using this two-dimensional array. So we do not have these continuous values stored on the computer. So currently we have only this representation of the sign function. Fine. So we have this representation of sign function that says that contains values as different points. So these are the points at which the values are stored. So at 0, it's 0. At pi by 2, it's 1. So let's say this point is 1. So at pi by 2, it is 1. Fine. At 2 pi, it's again 0. At pi, it's again 0. And then again 3 pi by 2, it's -1. So let's extend this axis here. And this point is -1. At 3 pi by 2, the value is -1. And then again at 2 pi, it's 0. So now we only know a few points at which now this is the function that is actually stored in the uh, mm, this is the function that is actually stored on the computer. And these are the known values. So these are the points at which we know the function of this, the values of this function sign. Now let's say we want to compute the value of this function at this particular point. At this point, how would we compute? Or let's say at this point, or how can we compute? Because we only know the values at a specified locations. So for that, we can use interpolation. So let's say we use linear interpolation. So we can simply approximate it like this. Okay, sorry, there is a right. So then we can use a linear function to approximate, and then we get the function of sine here. So in actual, the actual curve goes like this, but we are getting an approximate value like this. So we are not getting the exact value, we are getting an approximate value. So let me draw another graph to show this. So this was our actual sine function. Okay, sorry. This was our actual sine function, but what we ended up was So what we ended up storing was this, these only these values, the function values only at these points as discrete values. And then we reconstructed the function from this using a using linear interpolation, let's say. So we are getting this function that is actually stored on the computer. So you can see for a particular point, let's say at this point, if you want to approximate the function using this stored version, we are getting some error. So we are not actual getting the actual value of the function, but we are approximating the function value at this particular point. So this is where interpolation is useful. This is one of the use cases where you can use interpolation. So interpolation is one of the most widely used applications in numerical algorithms for computer graphics in computers. So in general. So yeah, this is why interpolation is important. And actually, in this through this example, I also show you that these values are approximate. The values obtained through interpolation are approximation of the values that the function would contain. These are not the exact values. Fine. So there are some errors associated with these interpolation methods. And also here we see that we only have function values. We can only approximate the function values across this segment of the entire x-axis because we only have the function values between the between at the ends of these section. We can't approximate the function value at here, or here because we don't know this other end where what should be the value at the other end. So we can't approximate the function values using interpolation outside the given range. So that's why the answer is at the intermediate points. Fine. So let's go ahead and solve the next question. To solve a differential equation using Ranga-Kutta method, inputs from the algorithms are. So I hope every one of you is familiar with differential equations. If you aren't, just type in the chat box. And let's say we are dealing with ordinary differential equations. So everyone, all of you are familiar with differential equations? If you're not, then yeah, I hope everyone is familiar. So let's take an example of an differential equation, and then we will solve this question. So what an differential equation looks like? Every one of you is familiar with the formula Newton's second law. Let me. uh, Newton's second law of motion that says force equals to mass into acceleration. So every one of you know that. So let's say we have a point particle with known mass. So let's say we have a point mass particle with a known mass. Fine. So we have a point mass particle with a known mass, that is m here in this case. And let's say we want to simulate its motion using the second law of motion given the initial position of the particle and forces are known at E, known every time. So how we will solve this problem? So we can solve this problem by discretizing the problem. So every one of you is familiar with the simulations. So every one of you is able, every one of you have played computer games. So how do they work? So basically what they do, they generate anime simulations based on some laws. So these simulations are, they are basically animations, and these animations are generated using simulations of differential equations, simulating differential equations, and we will see an example of how this Newton's second law of motion can be used for generating those animations. So essentially, what they are based on is based on time stating. So the equation can be solved using time stepping. So essentially, we write this function in terms of uh, differentials. So basically, we can write acceleration as rate of change of velocity. F equals to m into dv by dt, and then velocity can be written as velocity is equals to dx divided by dt. So this is a differential equation that can be used to solve this problem to simulate the motion of this particle. So this is how a differential equation looks like, and there are various methods to solve this differential equation in discrete domain. So let's see what the problem says. To solve a differential equation using Runge-Kutta method, what are the necessary inputs from the user? So what are the necessary inputs we needed here? So we needed the mass of the particle for this particular example. Then uh, we need the initial position. So we need the initial value of y. So let's say y is representing a position, then um, so y, so initial value of y. And then we also needed these differential equations to actually time step. So we need the differential equation in the form of x and y, the time size. So yeah, we also need the time step. So what is dt here? What would be that? So we are actually using time stepping. So we need the time size, and then we need the initial value of y also. So the correct answer is option D, all of the above. So let's put in the answer here, option D. So we need the different differential equation, the step size, and initial value of y to solve the differential equation. Fine. This is how we solve this problem. This is the answer for this question. So anyone, do you have any doubt regarding this Runge-Kutta method? If you have, just type in the chat box so that I can explain. So it's pretty important for you to understand this. Then only you'll be able to solve problems using C. So every one of you is familiar with the Runge-Kutta method. What is the code for this problem? So yeah, we will be looking at the code in the next question. So that we'll be looking forward to. So I hope every one of you is familiar with the concept behind the idea of differential equations and how Runge-Kutta method is used to solve this equation. So essentially how it works is, let's say we have a function f that depends on x comma y is given in a differential form. So let's say we have a function given in a differential form dy by dx. So let's say we know a function fxy that is given in the form of dy by dx, and we know what is the function value at uh, 0. So what is the initial function value? So let's say we call it something like 0. Let's assign the value 0. So let's see how what we are actually talking about here and how we will solve it. So for example, let's say I am giving you a function. Let's take a linear function, function in one variable. Let's say the function is fx equals to x. Um, mm, so this let's take a function y equals to x, and so how would I explain this? So let's come back here. So yeah, just give me a moment. I'm just thinking of what the best way to explain this. So you may also you should the best way would be go to the class lectures again and then see what is going on. I will just give a brief overview. So yeah. Mm. So yeah, you should go to the class lecture to know what actually it works, looks like, how to solve, why, how we solve using differential equations. So essentially, if you know the function value at y equals to 0, and you know the derivative. So let's say you know the function value at this point, and you know the slope of this function. Let's say you know the slope of this function. The slope of this function goes in this line, and you want to know the function value at y equals to time equals delta time t. Then what you can do, you can simply approximate it using a line, and then you will get the function value at this. It's equivalent to computing the area of this region. So this you must have been taught about in the class. So I would not get into the details because it would take too much of time for this session. Fine. So let's go ahead and solve the next problem. So I can give a small example here. So we all know that velocity is equals to rate of change of position or of displacement. So v equals to dx by dt. Now let's say we know velocity at t equals to 0. Let's say we know the velocity at this point. So we know velocity at t equals to 0. So let's say it's 0. We want to compute velocity at t t equals to t. And we know this differential equation that actually solve this problem. So we know this relation. Oh, sorry. Hmm. Huh. So we know this differential equation here, and we want to know time velocity at time t. So what you do, you simply integrate this. So you integrate this function d. So so you take dt here. So how to solve this? So you simply what you say, you bring dt here. So v into dt, you integrate this. So I don't know how to bring the integration symbol here. Integrate v dt equals to integrate. So this is how you solve this problem. No? Every one of you is familiar with this stuff. From t equals to 0 to t equals to t. Then what it how the how what the actual integration becomes? It becomes integration of v dt with respect to t is v into. So it's basically, so let's say we are every one of you is familiar with the forward Euler. Then v it equals to v equals t at t minus v at t equals to 0 equals to, and let's say we integrate this. So what it will become, on the right hand side it becomes position. On the right hand side the integral bounds are x at t0, x at t equals to 0 to x at t equals to t. So it becomes, hmm, so it essentially becomes this x at t equals to 0, x at t equals to t minus this, fine, and multiplied by del dt, yeah, into dt, into t, basically dt is t. So this is how what the equation looks like, how we are discretizing and solving this equation using forward Euler. So to solve these types of equations, we need these integration methods. So these are actually used to solve the problem. So this is Ranga-Kutha method is higher fourth order method to solve this kind of differential equations. So you have been taught about this in the class lectures, so you can go there and see. So it essentially requires the differential equations and then the step size and the initial value. Fine. So let's go ahead and proceed with the next problem. Lagrange polynomial passes through three data points as given below. So we are given, so here we are talking about interpolation here. So we are talking about Lagrange interpolation. So yeah, so as the term says, interpolation. So we are trying to find function values as some unknown inputs. So these are the known inputs. So at x equals to 5, the function value is 15.35. At x equals to 10, the function value is 9.63. At x equals to 15, the value is 3.74. And we want the function value at x equals to 7. So what would be the answer? So let's see how to solve this problem. So, the polynomial is determined as f of x, f of x. So yeah, let me switch things a bit so that it would be easier for me to write equations. Fine. So let's write some equations for this. Hmm. So yeah. Huh. So the polynomial is given as f of x equals to, so since we know the function values at three different points, so we have three coefficients for the polynomial. So L, so where is subscript? L at 0, at x into function value at x0, at x0. So yeah, this is plus L at 1 into function value at L at 1 at x into function value at x1. So these x1, x2 are the known function values. Values, at least the function value is known, plus L, and we'll see what are these L, how to estimate the function value L, and then again at x into function value at x2, x2. Fine. So this is how the Lagrange's polynomial looks like, and we are trying to solve the Lagrange polynomial interpolation problem here. Huh. So this is how the polynomial is determined. So this is point x0. So x0 is 5. So let's write this here. So let's put in the value here. X0 equals to 5. And then x1 is 10. So the next value that is known is, so 10. Sorry. So n equals to 10. and then x2 equals to 15. So these are the function values that we are dealing with here. Fine. So this is how the polynomial looks like, and we want to compute these values. And the values Lx is given by. So let's compute the next values that we want to compute here. Um, so L, let's say, where is this? Lj at x is given as product. So we need a symbol, product symbol here. Product one. This one, the product. So yeah, product 0. Okay, we don't need this. We only need this subscript. 0 greater than equals to. So we again need the symbol. So greater than equals to 0, less than equals to k. Let's say there are k points. M not equals to j. The product of. Let's write the product. So it's a division. So we need a structure here and this fraction. So x minus x m divided by xj minus xm. So xj minus xm. Fine. So let's insert the equation. So this is what yeah, this is how Lagrange's polynomial interpolation works. So basically, the polynomial is determined as like this: fx equals to L0x into f at the first known point, that is x0, then L1x into fx, the first known point, that is x1, and then L2 into function value at the second known point, that is x2. You need to put in the value of x in this function, and you will get the answer where Lj at x is given by this. So let's go ahead and solve this problem. So what would be L0 of x? So let's solve this. So what would be the value of L0 x? So L0 of x is x minus x0. So x1, we can't use j. So x. So let's correct this a bit. And then xj. J is basically 0 here. So x0 minus x1. This multiplied by x minus x0, 1, 2. So this would be L0, and we can put in the values like this. So x is 7. So 7 minus x1 is 10 divided by x0 minus x1 would be 5 minus 10, that is minus 5. This overall multiplied by so let's write in the next line. So equals to, so this will become x minus x1 will be 7 minus 10, that is minus 3. 7 minus 10, that is minus 3. And then x0 minus x1, that is x0 minus x1 is 5 minus 10, that is minus 5. Then again, x minus x2 is 7 minus 15, that is minus 8. And then x0 minus x2 is minus 10. So this will the value of L0x. So the answer 8 3 are 20, so this will equals to 24 by 50. So 48 by 100, so 0.48. Similarly, we can compute L1x and L2x. So let me just write in the values here. So L1x is, so L1x would be 7 minus L0, that is 5. So 2 divided by uh, x1 minus x0. So x1 minus x0 would be 5. And then again, it would be 7 minus x2. x2 is 15, so minus 8 divided by x1 minus x2, that is minus 5. So this will be L1x, which is equals to 25 and 16, 25 4, 16 for the 64. This will be 0.64. And then finally, we can compute the value of L2x. L2x would be 7 minus x0. X0 is basically 5, that is 2, divided by x2 minus x0, that is 15 minus 5, that is 10. Then the next term would be 7 minus x1. 1 is 10, so minus 3. And then x2 minus x1, that is 5. So this will be L2, which is equals to 3 to the 6 to the 12 minus 0.12. So the final value of fx would be, then you can write in the value of fx. So f of x is equals to, let's multiply and solve. So we know the values L0x, that is 0.48 multiplied by 15.35, 15.35 plus the next value is 0.64, 0.64 multiplied by 9.63 plus 0.12. So it's minus 0.12, 0.12 multiplied by 3.7, 3.74. Fine. So let's see what this value would be equals to. So this is equals to, we can use a calculator to solve this. So even I don't know if we are doing this correctly, but we can check. 35 plus 0.64 into 9.63 minus 12 into 3.74. So I hope all the values are correct. So 13.08. So correct answer is, solution is option B. So yeah, our answer is correct, 13.08. So the correct answer is option B. Option B. Fine. So this is the correct answer for this question. So let me go ahead and paste this answer where it is required. So write this. And then you can go to the online. Paste this figure here. So yeah, this is how we solve this problem. So yeah, everyone, do you have any doubt in this? So it's basically a simple formulation. So essentially, the function is determined is like this: the polynomial function fx equals to product of some terms, and then we compute the product, compute the values like this. So it's basically a numerical method to compute interpolate. So anyone, do you have any doubt regarding this problem? So we can write a code for this also. And I hope by now you all are able to solve this. You can write this code by on your own. If you can't write code, then you can type in the chat box and I will help you out. So anyone, do you have any doubt regarding this Lagrange's polynomial interpolation? So I hope using these formulas, you will be able to write up the code for this problem. If you can't, just type in the chat box and I will guide you to how to write the program for this. So no one is typing in the chat box. So just can you confirm if everything is fine, that there are no technical glitches, and then I believe every one of you have understood the solution. Anyone who's confused right now? So let me tell you, for the sake of this course, this is just a formula that is used for doing some interpolation. So let's say you have known function values and you want to compute the function values at unknown points. So this is the formula that you will be using to compute the formula. So these two fx and ljx, these two are important functions that you will be using to write code for interpolation. You don't need to understand the mathematics behind why these functions are like this right now. You just need to understand, for let's say we are giving you a function like this. Can you write up a code for this? Can you write up a code that solves this function numerically? So I'm just asking you guys this. Can you write up a code for this given function? If you can't, then I will code it up for you guys right now. So everyone, can you just anyone just type in the chat box, please, that you understood and you can write up the code. Am I audible? Mm. So I am audible. Huh. If we use a formula, if the code will run. So yeah, Gaurav, what do you want to say? Can you just elaborate your query? Okay, so you are saying, let's say if we know only 3 points, then only your program will run. So you are saying, let's say there are two more points, then how would you write a code that accommodates any number of points? That's what you are asking? Gaurav, can you just correct me if I'm thinking correctly, what you are asking? So you are saying for this problem, we knew only 3 points. So let's say we are giving another problem with 4 points. So if we write a code, can we write up a code that can accommodate any number of points using and solve the interpolation problem using Lagrange's polynomial? So you are asking that, can we write such code, or you are saying something else? Huh. So yeah, we can write up a code like that. So do you have any idea, or do you need me to help you out with that? That's what I'm asking. I'm just asking, do you have an idea to write that code or should I help you out? So let's see, even can we do it? Okay, so you want some hints. Fine. So let's solve this. Let's break this down into two parts. Though, so the first part is this function, like you know this function, right? No, fx. So how can you write the value of fx? No. So let's write the formula for this and let's see how you will write the code for this. Let's go ahead. So there are two basic formulas for this function solving this problem using Lagrange's polynomial. Hmm, let's write the formula here. Hmm. So you know f at x can be given as summation of. I need the summation function. Is the summation is not summation integration summation anything here? Huh, there should be. Yes. Now let's start. So let's divide this form of Lagrange's formula into two parts. So fx equals to, and then no, this. So yeah, k, let's say I equals to 0 to, and I can use this instead. Hmm. Hmm. I equals to 0 to k. Let's say there are total k data points. What's this? Why it's so big here? Y equals to 0 to k, and then we want to find the sum L at I multiplied by L at I at x multiplied by f at x at I. So this is the what the first function looks like. Is it gone? Okay, I will have to write the equation again. No problem. Hmm. So yeah, what I was saying f at x, f at x is given by a summation of. So I need the summation operator here. So let's put this here only. Hmm. So I need the summation operator here. And then I equals to 0 to I equals to 0 to k minus 1. And then L at I at x multiplied by f at x at I. So let's go ahead and insert this. So this is the function that we are talking about right now. So this is the polynomial that would give us the function value at a particular point. And the second equation is this equation that gives the value of L at, what do we say? L at J, L at J at X equals to product. So we need the product symbol here. We need the product symbol here, and then product underscore 0 less than equals to M less than equals to less than K, sorry, less than K. We want to find the product of a fraction that is given by this thing x minus x m divided by xj minus xm, xj minus x m. Insert. So let's go ahead and insert it. So let's fine. So this is how these are the two functions that define the Lagrange's polynomial. So Gaurav, now you can use these functions to solve the interpolation problem given any number of input points, because we are using the iterator I to iterate between 0 to k minus 1, where k is the total number of known points. Then for each of these individual values, so we know f of xi is I equals to 0 to k m minus 1. And then for each li of x can be computed using this formula. So I hope now you can use these formulas to solve this problem. So Gaurav, will you be able to write the code for this now? So this is how you will be writing the code for Lagrange polynomial interpolation for any number of points. Yeah, fine. Great. So let's come back to the topic. So let's paste that figure here. So yeah, we are done with this problem. Let's go ahead and the next problem. Accuracy of the trapezoidal rule increases when. So everyone, are you familiar with the trapezoidal rule? So let me give a brief idea of what is trapezoidal rule. Let's take the color as black here. So let's say we have a function looking like this. This is the x-axis, this is the y-axis. Sorry, this is f of x. That's fine. And let's say the function looks like this, and we want to compute the area of this function. So let's make it a bit like this. And let's say we know the function values at these points, and we want to compute the area of this function. So one of the most correct way is get an analytical function of this function, equation of this function. So get an analytical equation and then use integration to just integrate between the bounds A. So let's say bound A and B. So just do integration between the points A and B. And then, yeah, if you know the analytical equation, let's say we are trying to compute f(x) equals to x square between 0 to 1. So you can compute the area using basic integration, right? So you can compute this equation if the function is known. And let's say we don't know the analytical equation, but we know the function values at different points. So these are the discrete points at which the function value is known. So let me highlight those points with the color red. So let's denote these known points. The function values are known only at these points. We don't know the function value at any other point. The function values are known at these red crosses. So these are those points. So the trapezoidal rule is used to compute the area of such functions, discrete functions. So how would you compute the area of this function? So every one of you know the formula for computing the area of a trapezium. So basically what we do, we take the bounds of this function, a and b, draw a straight line at these points. So the function values at these points, and compute the area of this trapezium using the formula for the area of a trapezium. And this is known essentially known as the trapezoidal rule, and it gives an approximate area of this function up to some estimate. So it's not exact, but it's an approximation. So this is what the trapezoidal rule look like. So I hope every one of you is familiar with the area of a trapezium. So let's see how so in the let's see another example that will actually help us to solve our problem. So let's say the function looked like this. Um, a bit, let's say the function looks like this. Huh? So let's say the function looks like this, and we know the values at certain points. So we know the value at this point, then this point, then this point, then this point, then this point, and then this point. And let's say we use the single trapezium to approximate this function and compute the area. Fine. So this is the area. Then let's say we compute this formulation to compute the area of this function. So what is the error? What is the erroneous region in this area? What is the error in computing this area? So this violet region, so this region is the error in computing the area of this region. Fine. Now what we do, we let's say we use multiple sections, trapeziums to compute the area. So let's say we first compute the area of this region. Then we use this section and we compute the area. So we essentially divide the function into different small segments and use trapezoidal rule between those segments like this. And then this. Fine. So there are two different ways of computing the area of this same function. First, we use both the endpoints to compute the area. Second, use all the points and divide the function into small segments and then compute the area of smaller trapeziums. In the second case, you will see the error is less. So numerically, if you will study the trapezoidal rule, you will see that increasing the number of segments will result in less area. So through the figure also you can see it's resulting as less erroneous region. So the correct answer is accuracy of the trapezoidal rule increases when integration is carried out for sufficiently large range. No. Instead of trapezoid, we use triangular rectangular approximation. No. Number of segments on increase. So yeah, correct answer is option C. So the correct answer is option C. So it's general. It's for most of all these approximation algorithms. Whenever you use more number of points, you get better accuracy. So this is question number 4. Approximation increases says with the increase in number of segments between the upper and lower. So this is the correct answer for this question. Anyone do have any doubt? So it's pretty straightforward. So I tried to explain you guys using this. Fine. So let's take a break for maybe 5 minutes and then we'll resume. So we have a few more questions. I guess 2 to 3 more questions to solve. And then I will start taking questions from you guys. Fine. So let's see what's the time on my Teams application. So it's showing 124 here. So on my desktop, it's 714, 1914. So we'll start at 1990. Fine. So stay tuned. So we'll meet 5 minutes. So, hi everyone. So, let's resume. Hmm. Just 1 minute. So, yeah, let's start. So, the next question says, let's resume. The next question says, solve the ordinary differential equation using Ranga-Kutta fourth order method. And the step size is zero point 0.2. So, let's see what the Ranga-Kutta method says. To solve this problem using Ranga-Kutta method. So, yeah, let's solve this. So a better way would be write up a code for this and then we'll put in the values for this and we'll see the answers. Fine. Or maybe no, you should be able to understand the logic. So yeah, let's write up the solution. Hmm. So let's say what the Rangakutta method says. The fourth order method. Right. So let me put in the equations. So let's say we are given an equation dy by dx. So dy by dx is equals to f of x comma y, and we know the value of y at 0 is equals to y 0. Fine. So let's say we know this. So given this, we want to find y at, want to compute y at any particular time t, let's say. Compute y at t, right? So so y at t, the Ranga-Kutta method says that y at t can be given as y at 0 for this problem, y at 0 plus, let's use division here, 1 divided by 6 multiplied by k1. We'll see what these values are. K1 plus 2k2 2k3 plus k4 multiplied by h, where h is the time. Fine. H, where h is the time step. H is the time. given here. Fine. So let's define the values of this function. So k1 is given by function value at x t. So basically x0 comma y0. So I hope 0.2. So yeah, just give me a minute. Hmm. So yeah, so hmm. And we want the value at y at 0.2. Hmm. So fine. Yeah, x0 is basically 0 here. Here I can write it like this, 0. Huh. This is the value of k1. Let's put in the value of k2. K2 is given by h by 2, 0 plus h by 2, so basically h by 2. So h by 2 comma y0 plus half, so 1 by 2 k1 into h. So k1 into h. So this is k2. Then we get the value of k3. K3 is given by h by 2, f of x at h by 2, then y0 plus k2 by 2 into h. So it's k2 by 2 into h. And then k4 is given by f of x at t plus h. So basically h, and then y0 plus k3h. So half is gone and it's k3h. So yeah, these are the values for different function values. So let us put in the function values. So we know dy by dx equals to, let's write f of x y here, comma y is given as cos x minus का x y cube divided by 5. So overall divided by 5. Let's say write it like this. So this is what f of x comma y looks like. Just let's put it in. Like this and then insert it. This is what f of x comma y looks like, and we want to compute these particular values. So let's see what is K1. K1 is f at 0, comma y0. So y0 is basically 3. So, now we will need a calculator here. And I believe we need a scientific one. More functions. Hmm. So I guess I will have to use an online one. So I need to compute cosine of, so I need to compute cosine of, let's give it on top. So x is basically 0. So it's, acha, x is 0. So cos of 0 is 0. Cos of 0 is 1 minus xy cube. So x is already 0. So 1 by 5. It's essentially 1 by 5. Then k2 is given by x is h by 2. That is 0 0.1. So it's so let's consider it in radians only. It's again right. So let's compute cosine of 0 0.1. And let's say what is in degrees cosine of cos of 0 0.1. Okay, so it's 0.99. So 0.99 minus xy cube. So minus 0 0.1 into y cube. So 309, 381. So overall, this value divided by 5. By 5. So this will become 8.1. So minus 8.1 plus 0.99 divided by 5. It will be equals to minus 1.422. 422. In this way, you can compute these two values also, and you will put in the values, and you will see that the answer is, solution is option. So the answer would be option B. So the solution would be option B. So you just need to put in the formulas and you will get the answer. Fine. So it's pretty simple. So I hope you will be able to do this. So let's put it in the solutions and then you can use it. Fine. So I hope you will be able to use these formulas to solve this problem. So let's go ahead and solve the next problem. So we want to compute the value of this function. 1, 2, 3 e raised power x ln x dx. Question number 6. It's question number 6. The value of integral 1 to 3 e raised power x ln x dx using trapezoidal rule using 5 sub intervals. So so essentially the range is given to that gives an idea of the error. So we need to divide it into 5 subintervals. So delta x would be, so basically h here would be 2 divided by 5. The h would be this. Then we need to compute the function using trapezoidal rule. So it's a pretty basic function formula. So the formula is like this. So use trapezoidal rule to get the answer. So I have explained the trapezoidal rule earlier also. So when you use this formula, you will see that the answer would be option C. The correct answer would be option C. So you can use I hope you can use the pretty standard trapezoidal rule to solve this problem. I don't need to solve this problem again for you guys. Like it's a pretty standard formula. You can use it. So let's move over to the next topic. So I'm skipping these questions because we have a pretty another topic that we need to cover in this session. That is recursion. So I hope every one of you is familiar with recursion, and let's go ahead and solve a few questions on recursion. So yeah, consider the recursive C function that takes two argument func unsigned int n and there are two unsigned integers n and r that are taken as input, and let's see what we have to do, what the function does. It's a recursive function, so else return 0. So if n is greater than 0, return 1, return 0, and then let's see what is the input and we'll solve it step by step. So what is the return of the function foo when it calls at func 503 513 comma 2? So let's see how it goes. So we are calling func 5113 comma 2. So what it will call, so n is 513 and it's greater than 0. So this case will be executed. So what we are returning, so it will basically return n modulo, so 513 modulo r is 2 plus, again it's calling func n divided by r, so 513 divided by 2 comma 2. So yeah, this is what the function will return, and let's see what this function returns here. It again n is 513 by 2, which is equals to it will be 513 by 2 would be 513 be 256.5, so it will be 256. So it is 256 comma 2. So let's see what this function will return. It will again n is greater than 0, so it will be 256 modulo 2 plus func of n divided by r. So 256 by 2 is 128 comma 2. So again we will go to the stack will load up and we will solve this problem. So it will be 128 modulo 2 plus func of 128 divided by 2 is 64 comma 2. So again we will solve this. That will return in 64 modulo 2 plus func of 64 by 2, that is 32 comma 2. Again, how we will solve? We will 32 modulo 2 plus func of 16 comma 2, and again it will go like 16 modulo 2 plus func of 8 comma 2. So it goes on and on and on until the base case is met. So let's put it here for the sake of clarity. Fine. Fine. So now again, this will be solved. So it will be 8 modulo 2 plus func of 8 modulo 2 plus func of 8 divided by 2, that is 4 comma 2. Then again you will solve this problem. 4 modulo 2 plus func of 2 comma 2. Again n is greater than 0, so it will be 2 modulo 2 plus func of 2 divided 2 is 1 comma 2, and then lastly what you will see, it will return 1 modulo 2 plus func of 1 divided by 2 is 0 comma 2. So it will return the base case value. The base case value is 0. So this will return 0. So it will become equals to 0. So this is essentially 0 here. So let's put it here and then equals to 0. Oh, sorry there. And then yeah. So this is returning 0. 1 modulo 2 is 1. Yeah. Then 2 modulo 2 is 0, and then this value is 1. So this will be 1. 4 modulo 2 is again 0. This is 1. 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 And this becomes 1. And finally, 513 modulo 2 is 1 plus 1 equals to 2. So the answer is 2, option D. I hope I have done it correctly. So yeah, the solution is option D. So I hope you get it, how I'm solving this recursive problem and how we get to this answer. So if you have any doubts, just type in the chat box, or we can just end this session by solving the last question for this session. So anyone, do you have any doubt regarding this question? How are we solving this recursive problem? You can just type in the chat box. If you don't have, then we can proceed. So I believe no one has any doubt. So let's go ahead and solve the last problem for this session. So what is the output for this problem? So this is the function. If n equals to 4, return this. If n else, return this. And this is the main function. So again, this is an recursive program. So let's go ahead and solve this. So what we are saying, we are calling fun of 2. Fun of 2. So fun of 2, how it will be solved. So if n equals to 4, return n, else return. So it's not 4, then it will return 2 into fun of n plus 1. So it will 2 into fun of 2 plus 1, that is 3. Then again, 3 is not equals to 4, then again it will return 2 into fun of 4. And now fun of 4 will return n, that is 4 equals to 2 into 4. So it will be 8. So it will be returning 2 into 8. And finally, it will be returning 2 into 8, that is 16. So correct answer is option C. So solution option C. So 16 is the correct answer for this problem. So anyone, do you have any doubts regarding this question? If you have, just type in the chat box. Otherwise, we can wrap up this session for today. And if you have any doubts regarding any of the questions, you can type in the chat box. I have some few extra questions for you guys, programming practices that you can solve, and then we will discuss these problems in the next session. So if you have any doubts, just type in the chat box. Otherwise, we will end the session. So anyone, do you have any doubt regarding this problem? So anyone, any doubt regarding this session, you can type in the chat box. If you have doubt, you have a doubt in recursive functions, then you can type in the chat box. Otherwise, we can end the session. So I'm here till date. So there are 10 minutes left till the end of the session. So if you have any doubts, just type in the chat box. And after that, I will end the session.
So I believe none of you have any doubts. So let's end this session for today. So let's meet for the last session. That will be, I mean, second last session that will be held next week, and then there will be an extra week session on Sunday, next Sunday. So if you have any doubts, please come be prepared with your doubts.